A radioactive element, atomic nucleus X of mass 235 and number 292 decays into Y with mass 231 and number 91. Which of the following particles are emitted? So we have X 235 92 releases an alpha to form X 231 and 90, but it is Y 91. So releasing an alpha particle increase the atomic number. So X will become 91 and 231 by releasing an electron. So option A is the correct answer. The atomic number of an element having the valence shell electronic configuration as 4s2 4p6 is. The complete electronic configuration would be 1s2 2s2 2p6 3s2 3p6. This is the electronic configuration of argon having 18 electrons. Then comes 3d10 4s2 and 4p6 according to Aufbau's principle. Hence the number of electron is equal to number of proton, which is equal to 36 as the atomic number. So option B is the correct answer. The ratio between the neutron in carbon and silicon with respect to the atomic mass 12 and 28 is. The number of neutron in carbon 6, atomic number and mass 12 is 6, and neutrons in silicon having atomic number 14 and mass 28 is equal to 14. So the ratio is equal to 6:14, which is equal to 3:7. Option C. Which one is the correct configuration of chromium? We know that chromium has atomic number 24, so the configuration will be argon having 18 electrons, then 3d5 and 4s1. Because half-filled orbital are more stable than full-filled or paired orbital, so we can write this as D with half-filled 5 electrons and 4s as 1 electron. Option C is the correct answer. Which of the following electronic configuration is not possible according to Hund's rule? According to Hund's rule, all the electrons which are being filled should be singly or unpaired. So in this 1s2 2s2 there are 2p6 electrons. The electron should be first filled individually in each subshell. So if there are 3 electrons in p subshell, so first there should be unpaired electrons, as the unpaired electrons have high energy orbitals. So 2px2 cannot be possible, so it has to be, let's consider this as px, py and pz, and it has 2 electrons, so one should be with px and one should be with py. Px cannot accommodate 2 electrons simultaneously pairing, so option D is not possible according to Hund's rule. Penetration power of proton is A more than electron, B less than electron, C more than neutron, D none. So proton is 1837 approximately times heavier than electron. So penetration power is inversely proportional to mass. So penetration power of proton is less than electron. Option B is the correct answer. Which of the following particle has more electron than neutron? A is carbon, B fluorine, C O-2, D Al3+. Oxygen -2 having atomic number 8 and mass as 16 have more electrons than neutron. So your proton is 8, electron is 10 and neutron is equal to 8. So option C is the correct answer. Compared with an atom of atomic weight 12 and atomic number 6, the atom of atomic weight 13 and atomic number 6 will have. So let this be atom with atomic number 6 and weight 12, X be 6 and 13. Both are isotopes but have different number of neutrons. For A, proton is equal to 6, electron is equal to 6, neutron is equal to 6. And for X, that is B, proton is equal to 6, electron is equal to 6, but neutron is equal to 7. So option A is the correct answer. Carbon monoxide has same electrons, or the ion that is isoelectronic with CO is. Isoelectronic will have equal number of electrons, so CO has 6 plus 8, 14 electrons. Cn minus, that is cyanide, will have 6 plus 7 plus 1 extra electron is equal to 14 electrons. So these two species are isoelectronic to each other. Option B is the correct answer. Chlorine atom differs from chloride ion in the number of A proton, B neutron, C electron, D proton and electron. Chlorine and chloride atom differ in number of electrons. Chlorine has 17 electrons. Chloride has 18 electrons with complete octet. So option C is the correct answer. The nucleus of the element having atomic number 25 and atomic weight 55 will contain. The number of proton is equal to atomic number is equal to 25, and the number of neutron is equal to 55 minus 25 is equal to 30. So it will have 25 protons and 30 neutrons. Option A is the correct answer. The first Bohr radius of an atom with Z equal to 82 is R. Radius of its third orbit is A 9R, C 3R, B 6R, D only R. We know that the formula for radius is R is equal to n square upon m into h upon 2 pi the whole square into 4 pi epsilon 0 upon z e square. So from this formula, we know that R is directly proportional to n square. For radius in first orbit is R is equal to n square R, and Z is equal to 82 given, which is also a constant value. We know that for first orbit it is this. So for the third orbit, we can write n square R is equal to 3 square R, which is equal to 9R. So option A is the correct answer. If in nature there may not be an element for which the principal quantum number n is less than 4, then the total possible number of elements will be A 60, B 32, C 4, D 64. So for n is equal to 1, maximum number of states will be 2n square is equal to 2, and for n is equal to 2, 3, 4, maximum number of states of 2n square will be 8, 18 and 32 respectively. Hence, number of possible elements will be 2 plus 8 plus 18 plus 32 is equal to 60. As the n is only 4, there won't be any element greater than 4. So option A is the correct answer. The kinetic energy of electron in an orbit is radius r in hydrogen atom is with electric charge E. So we know that radius is r, electric charge is E. We have to find the kinetic energy. We know that potential energy in nth orbit with radius r and hydrogen atom H is equal to minus E square upon r. This is in CGS. Since kinetic energy is equal to half into potential energy, which is equal to kinetic energy is equal to E square upon 2r. So E square upon 2r is our kinetic energy. The ratio of energies of hydrogen atom in the first to second excited state is A 1 by 4, B 4 by 9, C 9 by 4, D 4. First excited state, that is second orbit, n is equal to 2. Second excited state, which is third orbit, where n is equal to 3. Since energy is equal to minus 13.6 upon n square, therefore ratio E2 upon E3 will be 3 by 2 the whole square, and it is inversely proportional to n square. 9 by 4 is the correct answer. An electron jumps from fourth orbit to the second orbit of hydrogen atom, given that Rydberg's constant r is equal to 10 raised to 5 per centimeter. The frequency in hertz of the emitted radiation will be. So we have to find the frequency. We know that 1 upon lambda is equal to r, that is Rydberg constant, is equal to n2 square minus n1 square. So we can write n2 and n1 as 2 square minus 1 upon 4 square. On solving, we get this is equal to 3r by 16. Therefore, lambda is equal to 16 upon 3r on rearranging. Substituting the value of r, we get 16 upon 3 into 10 raised to minus 5 centimeter. Now frequency n is equal to c upon lambda. We found out the value of lambda from here. C is speed of light, 3 into 10 raised to 10 divided by 16 by 3 into 10 raised to minus 5. On solving this, we get n frequency as 9 by 16 into 10 raised to 15 hertz. So option C is the correct answer. The ionization energy of the electron in hydrogen atom in the ground state is 13.6 eV. The atoms are excited to a higher level to emit radiations of 6 wavelength. The maximum wavelength of emitted radiation correspond to the transition between. So you know that number of wavelength is equal to n into n minus 1 upon 2, where n is equal to number of orbits from which the transition take place. So the maximum number of wave is equal to 6, so n into n minus 1 upon 2. On solving this, we get n is equal to 4. In all the options, wavelength of the emitted radiation will be maximum for transition n is equal to 4 to n is equal to 3. So option D is the correct answer. The ionization energy of 10 times ionized sodium atom is. We know that energy of ion, which is sodium ion, is equal to Z square into energy of hydrogen ion. So we know that sodium has atomic number Z is equal to 11 into 13.6 eV, which is the energy of hydrogen. So option D is the correct answer. Radius of electron's second stationary orbit in Bohr's atom is r. The radius of third orbit will be. So we know that radius r is directly proportional to n square. So Rn is equal to 2 upon Rn is equal to 3 can be written as 4 upon 9. Therefore, Rn is equal to 3 is equal to 9 by 4 into R. On solving, we get 2.25 R, which is R3. So option B is the correct answer. Consider an electron in nth orbit of hydrogen atom in the Bohr model. The circumference of the orbit can be expressed in terms of Broglie wavelength lambda of that electron as. According to Bohr's theory, MVR is equal to NH upon 2 pi. So we can write this as 2 pi r, which is the circumference, NH upon MV, where n can be written as n equal to lambda. as h upon mv can be substituted by lambda, which is the wavelength, de Broglie wavelength. So option D is the correct answer. The ratio of wavelength of the first line of Lyman series and the first line of Balmer series is 1 upon lambda is equal to R into 1 upon n1 square minus 1 upon n2 square. For first line of Lyman series, n1 is equal to 1 and n2 is equal to 2. And the first line of Balmer series, n2 is equal to 2 and n2, this is n1, this is n2, is equal to 3. So lambda Lyman and lambda Balmer can be written as 5 by 27. So option C is the correct answer. The absorption transition between the first and the fourth energy state of hydrogen atom are 3. The emission transition between these states will be, by using the formula for emission transmission, number of waves emitted is equal to n into n minus 1 upon 2. N can be substituted as 4 into 4 minus 1 upon 2, which is equal to 6. As it is 4 energy state, the hydrogen atom are 3. So we substitute n is equal to 4 because of energy state is 4, which is the principal quantum number. Option D is the correct answer. As per Bohr's model, the minimum energy in EV required to move an electron from ground state of doubly ionized lithium atom, that is Z equal to 3, is, we know that energy is equal to minus Z square into 13.6 EV. So Z is 3, so we can write it as 9 into 13.6 EV. On solving, we get minus 122.4 EV. So ionization energy is opposite of the total energy. So 122.4 EV is the correct answer. Option D. An alpha nucleus of energy half mv square bombarded on a heavy nuclear target of charge Ze. Then the distance of the closest approach from the alpha nucleus will be proportional to. So we have to find the distance of closest approach, which is equal to R0 is equal to Z E square upon 2 m v square pi epsilon 0. So this can be derived from the second Bohr postulate, which is equal to mh upon 2 pi is equal to mvr. Now from this we know that r is inversely proportional to the mass m. It is not inversely proportional to v raised to 4. It is inversely proportional to v square. It is directly proportional to z. So option A is the appropriate answer. Minimum excitation potential of Bohr's first orbit in hydrogen atom is, excitation potential is equal to excitation energy upon electron. So minimum excitation energy corresponds to from n is equal to 1 to n is equal to 2. Therefore minimum excitation energy in hydrogen atom will be, minimum excitation energy will be minus 3.4 into minus of minus 13.6. This is plus 10.2 eV. So minimum excitation potential will be 10.2 eV upon electron. So electron goes, so 10.2 volt. Option C is the correct answer. In a hydrogen atom, the distance between the electron and the proton is 2.5 into 10 raised to 11 meter. The force, electrical force of attraction between them will be, so we know force is equal to K Q1 Q2, which is charge 1 charge 2 upon R square. On substituting the values, we get force is equal to K, which is constant, 9 into 10 raised to 9 into charge of one electron into charge of another electron divided by radius or distance 2.5 into 10 raised to minus 11 the whole square. On solving this, we get force is equal to 3.7 into 10 raised to minus 7 Newton. So option B is the correct answer. In Bohr model of hydrogen atom, the ratio of periods of revolution of an electron n is equal to 2 and n is equal to 1 orbit is. We know that period of revolution is directly proportional to n cube. Therefore, T2 upon T1 is equal to 2 cube upon 1 cube. So which is equal to 8. So option C is the correct answer. The ratio of minimum to maximize wavelength in Balmer series is, we know that 1 upon lambda is equal to R into 1 upon n1 square minus 1 upon n2 square. So lambda minimum upon lambda maximum of Balmer series can be written as 1 upon 2 square minus 1 upon 3 square divided by, for maximum, 1 upon 2 square minus 1 upon infinity. On solving this, we get 5 upon 9. So option A is the correct answer. Orbital acceleration of electron is, we know that mvr is equal to nh upon 2 pi. So v is equal to nh upon 2 m pi r. This is from second Bohr postulate. So we can write v square upon r, which is acceleration, is equal to n square h square upon 4 pi square m square r cube. Square the equation this with velocity. So the corresponding option is option A. Which of the following transition will have highest emission wavelength? For highest emission wavelength, we know that since energy 2 is less than energy 1 and lambda 2 is greater than lambda 1. So for highest energy, let there be 5 levels of energy: N5, N4, N3, N2 and N1. So from energy level 5 to energy level 2, this is E2 and lambda 2. And for E1 to lambda 1, which is the minimum energy level. So the transition for highest emission of wavelength will be from N5 to N2. The maximum gap difference, option D.